Yeah.
I want to be reimbursed for pizza, so it looks better if there's names of who supposedly ate it.
You know, you can start.
Many, many things.
Yeah.
They should just dress it.
So you write down how many spices you guys want to do.
Yeah, everything.
Did you get it now?
Oh, yes. It's honest. Question? Okay, then pizza will be delayed, so let's start.
Can I get started? Okay, yes, so thank you for being here, everyone. I'm gonna tell you today about tidal interactions and compact binaries. This is a really vast topic, and there's no way I'm gonna be able to cover it exhaustively in an hour. So I will try and just focus on a few, I think, interesting results. To get started, let's just study the problem or formulate the problem that I have in mind. So let's imagine you have a compact binary which consists of like one neutron star or black hole that we will kind of focus on and a distant companion. Okay. Orbiting their common center of mass. For a first approximation, we're just going to model the orbit as a Newtonian circular orbit. And we're going to imagine that our compact object is just a perfect fluid sphere. Okay. What we're going to be interested in is the tidal influence of the second body's gravitational field on the compact object. Okay. I will run through treatment of this problem in Newtonian gravity to kind of motivate how things work in general relativity. Then I'll talk about basically how you define a notion of tidal deformations in the relativistic setting, how that impacts the gravitational wave observables, and then I'll also discuss the notion of tidal permeability for black holes and some other relativistic effects. So first things first, when are finite size effects important? So basically, you can get a sense of when the tidal interaction becomes important just by comparing the tidal acceleration. So, you know, the gradient of the tidal force across this body to the overall acceleration of the center of mass. So the acceleration of the center of mass is just going to be minus g m2. Let's call this guy m1, 2, and then let's call the orbital separation 2 r0. Okay, so this will just be 4 r0 squared. And then we want to understand how this varies at the center of mass versus the surface of the star. So if we just compute dAdr across the star or across the compact object, you get gm2 over r0 cubed delta r factor 2, and then delta r, sorry, like that. And then, right, and so then you can compare, so then rearrange this is what I want to do, rearrange here, consider the change in the acceleration at the surface with a small difference in the acceleration of the surface versus the center, and compare that to the overall acceleration of the body towards m2. And this is just delta r over r0 with a factor of 2, things like that. All right, but the point is that the tidal interactions become more important, unsurprisingly, as the bodies get close together. And if you want to estimate when is this order 10% effect, by my calculation for a binary neutron star merger. So here we're going to assume, just for the purposes of estimating things, let's assume M1 and M2 is they're each 1.4 solar mass neutron stars. And I think this is about a 10% effect at a separation of order, of order 50 neutron star radii, where R for a typical nuclear star is 12 kilometers, which is a gravitational wave frequency, twice the orbital frequency of order several tens of hertz. So that's with the basic Newtonian kind of back of the envelope calculation. When are relativistic corrections important in this problem? Basically, when some characteristic velocity v starts to approach the speed of light, and for the orbit, we can just write, the orbital velocity, which is this r naught, and then the orbital frequency, say omega, over c. And just for a Newtonian circular orbit, this is just going to be r naught over c times the orbital frequency expressed in terms of the total mass and the orbital separation. So you end up with b over c for the orbit being gm over c squared times the orbital separation to the 1/2, which for our canonical binary neutron star example is of order is of order 10% basically for these parameters, okay, for a separation of about 50 neutron star radii. The other thing we want to consider is when you have to treat the structure of the star relativistically. There you can again define a characteristic velocity inside, just as basically from the gravitational freefall time, okay, with the length scale of the neutron star. And so here, this works out to be the compactness of the star. So this is Gm, we call it M1 over c squared r to the 1/2. And for a neutron star of 1.4 solar masses and a radius of 12 kilometers, this number is 0.2, 1/2. So this thing is like 4 or something. Okay, so this motivates the fact that the compact object is compact enough to require relativistic treatment of its internal structure, and it motivates the fact that the orbital motion is relativistic. Okay, and so we expect the system to source gravitational radiation.
Sorry, is there normally the way I thought is V over C? It's true, V over C, but V over C to the square.
Yeah, so
Not the one on the left, the GM, GR contribution.
sorry, yeah, here.
Yeah, the GR contribution. Square.
No, so I'm just talking about what is how relativistic is the plus, just V over C.
Right.
Yeah.
Right. So if you want to compare the potential, higher.
Sure. So I just want this to motivate the fact that this system is going to be generating gravitational waves. Okay. So the thing I wanted to mention also about the tides is if you consider the time scale for the orbital motion. So the orbital period, we have the orbital frequency here. The orbital period is just going to be basically r naught cubed over g m total. 1/2. And then the hydrodynamical time scale inside the compact object is going to be r cubed over gm to the 1/2. So just related to this, sorry, this should be an m1.
Sorry.
Yeah.
Just so I make sure that I understand what we want to do here.
Yeah.
What you just said, the engine was that you were doing, but figuring out blankets relativistic to motivate what?
To motivate the thing that's going to come next. Okay, yes, sorry. So I'm just stepping back though to just get back to the tidal interaction itself. You can compare the time scale over which the companion is orbiting, right? Which is the time scale that its tidal influence will be varying, basically, to the time scale for the reaction of the fluid inside the star, which is the hydrodynamic time scale. Okay, and if you take this ratio, you find that it's going to you basically find that the orbital time scale, we can estimate it for these parameters, is of order a second at these separations, and this hydrodynamic time scale is of order 10⁻⁴ seconds. So this is motivating the fact that in the regime of interest, the fluid is going to respond near instantaneously to changes in the tidal field. And so you can treat the tides in an adiabatic regime where this compact object never leaves hydrostatic equilibrium. Okay, when this separation of timescales breaks down, then you need to treat things in the regime of dynamical tides. Okay, but for the configurations we're going to have in mind, we will work in the adiabatic regime where the object stays in equilibrium. Okay, so the thing I wanted to say next is what is the time scale over which the orbit is shrinking due to gravitational radiation. So let's look at that. So the quadrupole formula for gravitational radiation says that the power radiating gravitational waves is related to 3 time derivatives of the quadrupole moment of the system. Okay, and this is the orbital quadrupole moment. Orbital. Okay. And the quadrupole moment is going to scale like m. Let's see, m r to the L, so quadrupole is squared. And then we have 3 time derivatives. So this is going to scale like a frequency cubed, and then we have 2 of these things. So this is m squared r to the 4th, omega to the 6th, over 5 c to the 5th. Okay, and then there's some numerical factors that aren't very important. Here, we can think of this in an effective one-body picture where you have a reduced mass orbiting the center of mass. And so let's put in the reduced mass here. Okay, so this is the rate at which gravitational waves are carrying away energy from the system. If you compute a time scale from this, the time scale at which the orbit is going to shrink from a given radius r0 down to 0, this is something called Peter's formula. And you end up with a gravitational wave time scale that is of this order r0 to the 4th, 5th, u m total squared, which for our binary at that separation is of order like 100 minutes. So the radiation reaction time scale is not relevant for the tidal interactions we want to consider. We can take the orbit to basically be a fixed radius. Okay, so with that in mind, let's consider adiabatic tidal perturbations of this fluid body in Newtonian gravity. Let me write down, let me go over here maybe. So what are the governing equations for the system? We have right here, Newtonian. Okay, so the governing equations are Poisson's equation for the gravitational potential. And then we have Euler's equation, which is going to be relevant inside the fluid star. Okay. And if we just consider the fluid star in isolation, then we have, so it's static. So basically the velocities are 0, and the background solution for the unperturbed star, is just the usual U is Gm over R outside the star. And if you want to also have this hold inside the star, you can write it as 4 pi G integral over the density. Okay, so that's the background solution. Now we want to put in perturbation to the gravitational potential that is sourced by the gravitational field of the companion. So we're going to take U to U plus delta U, okay? But it will just be convenient to think of this perturbation delta U as having 2 pieces, one of which is the tidal response of the body, and one of which is the applied tidal field, which I'll write as V, and I'll just write this bit as delta U. Okay, so V is the field from the companion, and delta U is the response of this object to the applied tidal field. So then we can consider perturbations of these equations both inside and outside the star. Outside the star, basically the right-hand side of Poisson's equations vanishes, so we have Laplace equation, and this motivates an expansion of the perturbations in spherical harmonics. Okay, the boundary conditions for solving Laplace's equation would be different for the response and the applied tidal field, which is what motivated this separation. The applied tidal field is sourced by the companion, which is far away, so its gravitational field should increase radially as we move away from this object. It should be regular at the center, and it can blow up at infinity. And the response of the body should do the opposite, right? So its field, its potential should go to 0 at infinity. And so what this means is that when you solve Laplace's equation outside the star, you can just write down solutions in spherical harmonics for these things. So delta U outside is just going to be some sum over Lm. Okay, in terms of some moments ILM, which we'll call multipole moments. And it's going to have a behavior, as I was saying, that is decaying in R. Okay, so modulo some numerical prefactors. That's just the external solution. And then the applied tidal field is going to have the growing behavior. So it will have multiple moments ELM, and it will grow like R to the L. So generically, Laplace's equation, in the decomposition, we'll just have a growing piece and a decaying piece, and we just split that into these 2 parts of the perturbation. Okay.
So it's clear that the external perturbation cannot have
We are. You can view it as just there's some perturbation which has growing and decaying pieces, and we're identifying the growing pieces as applied tidal field. Yeah, so in this picture, that's right. So in this picture, you know, the companion is basically asymptotically far away, and we're working in the vicinity of the compact object of interest. But you can imagine doing some matching calculation where then you match onto an external space. That's right. That's a good point. And these sums, so for the applied tidal field, the sum over L begins at L equals 2, because the monopole moment is going to be spatially constant, and so it's not going to play any role in our equations here. And the dipole moment we can eliminate by transforming to the center of mass frame. So the physically relevant multipoles start at L equals 2. So this is the external solution. If we work now inside the star, the perturbed, we have basically the perturbations of these two equations. So we're going to have the perturbed Poisson equation by d delta rho, and we're going to have the perturbed Euler equation. So I'll just finish this Newtonian bit, and then maybe everyone grab theta. Over rho squared. Okay, so sorry, derivative of u. Yeah, so I think I'm just working with the opposite sign. Yeah. Okay, so we're going to consider stationary perturbations. Okay, basically because as I was mentioning, you know, we're taking the fluid to be in equilibrium at a given moment. Okay, so let's just consider stationary perturbations so that the time derivative of velocity perturbation vanishes. Then what we want to do to solve these things is to make a spherical harmonic decomposition. Okay, so there's basically three variables in the problem here. There's delta U. You can just write as some ULM. Okay, there's delta P. And there's delta rho, the pressure and density perturbation. And there are two equations, and so we need one other relation between delta P and delta rho. But this is supplied by considering, by basically defining a displacement vector for the perturbation. So what does this mean? If you consider some perturbation of the star, which takes you from one configuration to some new configuration, okay, something like that, you can define a vector which I'll call delta R, which is going to map one fluid element in the unperturbed star to the same fluid element in the perturbed star. Okay. But this mapping is not unique. You can imagine a case where if your perturbation is just expanding the star, let's say, you could have the displacement be purely radial, or you could have the displacement all go radially, but also a few degrees to the left or something. So there's some degeneracy in choosing what the displacement vector is. And we're going to choose to describe the displacement such that the Lagrangian change of the density during the perturbation is 0. What this means is that the density of the fluid perturbation is preserved under this map by the displacement vector. Okay. What this amounts to is a condition on the displacement vector, which you can think of as kind of like fixing a gauge. In this case,
That's only true if the displacement actually doesn't change.
So the mass is conserved.
Mass is conserved.
We're choosing the volume to be conserved by this choice of displacement vector. That's right. Yeah. And what this amounts to is choosing the displacement vector to be divergenceless. this case. And so that is the condition that gives you a relationship between delta P and delta rho. Choosing this delta R to be divergenceless, you can find that basically you can expand the Lagrangian perturbation in terms of these Eulerian perturbations, which instead of mapping from one fluid element to the same fluid element in the perturbed configuration, just look at how a spatially fixed point, how the density and perturbation, density and pressure change. And so if you work out what this condition means in terms of the Eulerian perturbations, you end up with the relationship delta rho is equal to the gradient of rho times the displacement vector. But I was saying we've chosen this thing to be divergenceless. And so the relationship you end up with is that the PLMs, where to put this, PLMs are minus P prime, sorry, yeah, PLMs are minus P prime times delta R over R. And then we have the background Euler equation, hydrostatic equilibrium, okay, which will tell us what P prime is. So this ends up being GM rho over R squared, delta R, J over R. Okay, and then you have rho LM being minus rho prime R, J over R. So the point is that.
Wait, at least some PLM.
Yeah, sorry, I
Suggesting that.
yeah, sorry. I should be consistent in using the LMs in places. So really, this should be PLM, and this I'll write as some moments of the displacement vector. So let's write this as okay. So this is true. Then this is true. Here you have the LMs. And then here, rho prime, and you have CLM. Okay. GM rho CLM over R squared now, because I scaled out one factor of R. Okay, so the point is, Poisson's equation involves, Euler's equation involves delta U, delta P, and delta rho. I think one of these was a delta rho. Now we have a relationship that expresses delta P and delta rho in terms of just the displacement vector CLM. Okay, so Euler's equation is going to give you a relationship between the moments of the tidal potential perturbation and the displacement vector. And this relationship just works out to be that the ULM are VM times the displacement vector moments over R minus R to the L, the moments of the tidal field. Okay, and then equipped with this relationship, which is coming from Euler's equation, you can plug this into the Poisson equation, where delta rho is also going to be expanded in terms of the displacement vector. And you end up with a first order differential equation that is going to specify basically what the displacement vector is. Once you've solved for the displacement vector, you can construct all the perturbations from that. Okay, so let's get back to it here. Just to recap, what I'm saying is you look at the perturbed Euler equation and the perturbed Poisson equation. These end up yielding a relationship between the perturbed variables in this displacement vector, which describes how you move in a Lagrangian perturbation from the unperturbed state to the perturbed state. When you plug the expressions that involve the displacement vector into the perturbed Poisson equation, you end up getting one differential equation for this quantity eta, which is the logarithmic derivative of the displacement vector. Okay, so this is d by dr of the displacement vector moments. Okay, so that's the logarithmic derivative. The equation ends up being independent of the spherical harmonic index m. So this tells you that the tidal response is going to be only L dependent, depending on the quadrupole moment. Okay, and you can integrate this numerically from the center of the star to the surface. And when you have solved for this, you basically have the displacement vector up to an overall scale, which ends up being unimportant for what we care about. Here, because what we're going to care about the multipole moments, which is what we want to calculate, and it turns out that you can determine the multiple moments not knowing the scale. So the scale does not enter, because we're going to calculate the multiple moments by matching the gravitational potential inside the star with the expression you have outside the star, because outside the star, that's where the multiple moments are involved here. And we want the potential to be smooth across the surface of the star. And so that gives you a condition, the potential has to be continuous in its first derivative has to be continuous. Instead of matching those two things separately, you can just match the logarithm.
Yeah, which direction are we taking our Z axis for spherical components?
I guess it's the Z axis would be aligned with the orbital angular momentum. Yeah, that's right. Yeah, so the neutron stars here are non-spinning. Okay, so yes, so here, by the way, this rho bar is just the average density for the star. And so this is how the density profile or the equation of state ends up coming into this relation to determine the displacement vector. So I was describing the matching procedure where now we have an expression for delta U outside the star here, and we have the expression inside the star that depends on this displacement vector. They have to match smoothly at the surface. And so that gives you a condition on the first derivative and the function value of this guy, which involves the multipole moments. So the matching procedure ends up producing a relationship for ILM in terms of these eta functions. And the relationship is just following. GILM is equal to minus 2 AL R to the 2L plus 1 ELM modulo some numerical factors that aren't important. And the thing I've defined here is called the tidal love number, KL. And in Newtonian gravity, it looks like this. So it just depends on the value of this logarithmic derivative of the displacement vector at the surface of the star. So the point is, going through all this perturbation theory, you end up with a single differential equation which determines the displacement vector up to an overall scale, which determines this tidal love number that tells you how large an induced, say, quadrupole moment is given some applied quadrupole moment. So ELM would be the E2 would be the quadrupole moment of the companion's gravitational field, and this would induce a quadrupole moment I2, whose amplitude is basically determined by this tidal love number. And in gravitational waves, we're used to talking about something called the tidal deformability. Lambda, that's just absorbing the factors of radius. You can write down now what the total gravitational potential outside the star looks like. So that's the background piece plus this delta U plus the applied tidal field. And it looks like this, sum over LM, 1 plus 2 KL, R over R, 2L plus 1. Okay, times R to the L, E LM. So there's a piece that grows radially, which is the applied tidal field, and there's a response piece, which is going to decay radially because there's an r to the minus 2 alpha plus 1. That's the structure of the gravitational potential. Okay, so let's move to the relativistic regime and see what changes and what stays the same. So in the relativistic regime, we want to work with the full space-time metric rather than just the Newtonian potential. You can think of the Newtonian potential as determining the TT component of the space-time metric, but there are going to be other metric components that get perturbed. And then in addition, we're going to have, instead of Poisson's equation for the gravitational field, we're going to have the Einstein field equations, and we'll have a relativistic version of the Euler equation. So let me quickly write this down. So let's do GR adiabatic times. So we have Einstein's field equations, we have the relativistic Euler equation. Whereas in Newtonian theory, we had the mass density rho. This is the total energy density that also accounts for internal energy. And this follows from conservation of stress energy for our perfect fluid model of the star. So the stress energy tensor is just that of a perfect fluid. Okay, so we're going to proceed the same way as in the Newtonian problem, where first there's a background solution, which is just going to be a Schwarzschild solution describing the space-time metric outside the star. And inside the star, we'll have some interior Schwarzschild solution given the perfect fluid, okay, given perfect fluid interior. Then we formulate perturbations. So our metric will get a perturbation. So the background metric is Schwarzschild. And it will get some perturbation, call it P alpha beta, okay, which again we can think of as having two pieces. One piece which is going to grow in amplitude radially, which is the tidal field, the applied tidal field, and one piece that is going to decay radially. Which we can think of as the body's response. You can write down the most generic possible metric perturbation. So let me first just motivate this. The background metric, let's write as PAB plus R squared omega AB. So the four-dimensional spacetime, we're just splitting into an angular part on two sphere surfaces and a part that depends on some time coordinate and some radial coordinate. Okay, where here GAP is just going to be in the standard Schwarzschild coordinates. It's 2m over r. Okay, I'm using G equals C equals 1 units. And then this is just the two-sphere metric. One squared. All right. So the most generic perturbation in this kind of splitting is going to look like. So there's some, time radius, or radius components, which we can write in a circle harmonic expansion. Inspired by the Newtonian structure, like this. there can potentially be pieces that mix the angular and transverse components. So this is a vector spherical harmonic. It's just the regular spherical harmonic, but there's an angular derivative. So this is something that lives on the two spheres. It's got a direction. It would be directions. And there's a second kind of spherical harmonic that you can construct. Okay, so all I'm doing is scalar vector and tensor spherical harmonic decomposition of the metric perturbation. So this is just a derivative of one of the spherical harmonics that lives on the two sphere. This is like a cross product of one of those derivatives, so that this thing changes under parity. If you change the orientation of your space, so like from a right angle to a left angle, this vector spherical harmonic will change sign, whereas this one will not. So the perturbations will generically have two classes, two parities. Some will be even parity and some will be odd parity under this kind of orientation change. And this is just a generic thing for tensor perturbations. Okay, and then we have the angular part of the perturbation with different tensor spherical harmonics, which you can build out of derivatives of the vector spherical harmonics, basically. Plus Ln. So there's even parity tensor harmonics of two kinds, and then there's one set of odd parity tensor harmonics. This is the most general perturbation that you can write down to our static spherically symmetric background. And this is what we want to plug into the Einstein field equations in the perturbed version, in the perturbed Euler equations. Before we do that, we have some gauge freedom that we can use to simplify this. So if you imagine making a small coordinate transformation to to the coordinates you're working in, and in the perturbed space-time, so you can make some coordinate change that describes your metric, and then you can absorb the effect of that coordinate change into your perturbation. This gives you some freedom in how you're defining the perturbation. Okay. Basically, probably, so I'm not going to work through it, but it gives you 4 degrees of freedom, 3 of which are even parity and 1 of which are odd parity. So you can fix your gauge and eliminate 4 of these perturbations by fixing your gauge. And just to do this calculation, I'll work in the Reggie-Wheeler gauge, which is a standard choice. Okay, and so you choose to eliminate this guy, this guy, this guy, and one of these, I believe. Double check. Yeah, so sorry, this is the 4th, because this is a vector. So this has 2 components, 1, 2, 3, and 4. Okay, so that gives you the metric perturbation. We plug it into the perturbed version of the field equations outside the star, where there's no matter source. And the solution, which is going to be akin to this multipole solution we wrote down, for the TT perturbation, so HTTLM, looks like the following. Okay, so what's going on here? Firstly, we're working at linear perturbation theory. So just like in the Newtonian case, the total potential, the total metric perturbation has to be proportional to the applied tidal field. So that's why there's this ELM, the moments of the tidal field here. The solutions to the field equations generically have some piece that is going to grow radially and some piece that's going to decay radially. So that explains the radial dependence. There's some piece that's decaying as a function of r, and there's some piece that's going to grow as a function of r. Then there's some unknown coefficient here, which we don't know what it is, but based on the Newtonian analogy, we can call this some love number, which we have yet to define. So there's just some coefficient to the decaying piece that is going to be a relativistic version of love number. And then these things here are hypergeometric functions, so they're like polynomials and with log terms. And those are given to us by the solution of the vacuum field equations. And they both tend to 1 in the limit of small m over r. Okay. Which recovers the Newtonian limit for this whole expression. But at this stage, we don't know what this coefficient is. We're just exploiting a parallel with the Newtonian example to say that it must be a love number. In order to calculate it, you have to solve for the internal structure of the perturbed neutron star. So you're going to have the perturbed version of the Euler equation, which, just like in the Newtonian case, is going to relate 3 things. Essentially, you're going to relate the TT component of metric perturbation, which is the analog of the Newtonian potential, and you're going to relate the pressure and the density perturbations. The pressure and density perturbations get related when you specify the displacement vector. So you'll go through the same exercise of choosing the displacement vector to set the Lagrangian perturbation and density to 0. That will provide a relationship between delta rho and delta p. And so the perturbed Euler equation is going to return a relationship between this HTT and your displacement vector. And that ends up being the following. So you find that delta r itself is e to the minus 2 psi, where this is the TT component of related gas, the TT component of the background metric times PTT over 2 psi prime. This is a radial derivative. So I put back in the circle harmonics to reconstruct things, but these are the circle harmonic moments of these guys, and you could have some CLM circle harmonic moments of these guys. So this is the output of the perturbed Euler equation. And then, just like in the Newtonian problem, you are going to plug this relationship into the perturbed Einstein equations, which gave you outside an analytic solution for the TT component of metric perturbation. But inside will depend on the fluid, will depend on its equation of state and the density and pressure profiles. So you can't get a numerical solution to that analytically, but you can write down the governing equation, and it's going to look almost exactly like the Newtonian equation. You crunch through this. So let me do this right here. When you crunch through this, you end up getting following. Maybe do that now. Then plus squared minus L plus 1. And this is times 1 minus 2 m over r, and I think there's a times 1 minus 2 m over r here. So the point is that this equation in the Newtonian limit of small m over r just recovers the Newtonian line. And you can solve it in the same way. And you can use that to determine your displacement vector up to an overall scale. And now, instead of matching Newtonian potentials across the surface, you're matching TT components of metric perturbation across the surface. But the mechanics are the same. And this provides you with a definition for KL in the relativistic context, which had appeared here. Okay. I won't write it out, but it reduces the Newtonian definition in the appropriate limit. So in the relativistic problem, by promoting the Newtonian potential to like a full metric perturbation. You get the same structure of the equations and you end up with a result that is the same up to relativistic fractions. Okay, let's now ask what happens for a black hole. So I was describing this problem in the context of a perfect fluid interior for the object. If it's a black hole, then the internal solution is also a vacuum solution. There's no right-hand side to the Einstein field equations. And the fluid perturbations in Euler's equations are zero. What that means is that this solution, which is valid outside the black hole, is also the form of the solution inside the black hole, because it's vacuum everywhere. And your matching condition at the event horizon, if you take that as a boundary, just has to mean that the solution is regular everywhere, right? From anywhere outside the singularity up to infinity, your HTT has to be regular because it's vacuum on both sides of the event horizon. When you look at this kind of solution, the decaying piece, this hypergeometric function B1L, ends up being singular at the horizon R equals to M. So the horizon of the Schwarzschild black hole. The only way to cure that singularity is to set the Love number to zero. So this is why black holes have zero Love number. Just a regular solution to the tidal perturbation everywhere requires that their decaying piece be zero. You might worry that we did this in coordinates that are singular at the event horizon, but you don't have to use Schwarzschild TR coordinates which have that singularity to do this calculation. You can use light cone coordinates that are regular across the horizon, and you find the same thing. You don't even have to do the matching at the horizon. You can do it somewhere else, but you will still find that intrinsically there is part of the solution that is going to blow up at the horizon unless the Love number is set to zero.
So is there some physical sense in this? Can get information about what
Yeah, so I think one way to say this is, the Love numbers aren't some kind of hair on a black hole that can be used to distinguish different black holes or something. There's no information. The other way to phrase this is that if you think of dividing this perturbation into a piece that is the applied tidal field, a piece that's the response of the black hole, there is no response. It does not acquire tidally induced multipole moments. The surface of the black hole will change because we have a non-zero displacement vector, right? So if you just imagine mapping R equals 2M to R plus delta R, where delta R is just this thing evaluated at R equals 2M, the shape of the surface will change. But far away, if you read off the gravitational field of the black hole, it is not contributing any multipole moments to that field because it's a vacuum solution. So the perturbed spacetime is just the background spacetime of the black hole plus the external tidal field with no additional contribution or back reaction to the black hole. Whereas if you had a neutron star, the tides are rearranging fluid elements, and that is causing a change in the external gravitational potential. So that's why black holes are unique. They have these zero tidal Love numbers. But the point that I wanted to make is that even though they don't acquire these tidally induced multipole moments, they still change their shape. They still deform tidally. And so there is a notion of the deformation of the surface of an object, which actually you can quantify in terms of a different kind of love number, which we'll call a superficial Love number, HL. In Newtonian theory for perfect fluids, they're just related in a simple way. But in the relativistic regime, there are relativistic corrections that make this an uglier expression. So the HL are non-zero for a black hole. In fact, H2 is 1/4, but the KL are 0. And it turns out that even for rotating black holes, the generalizations dissipate. These KL type things end up vanishing.
So also, how do you think of the implications of this for like scattering of the gravitation of the plate? Because I have a neutron star in a gravitational neutron star is a one.
Yeah.
So the external potential, there's a response. And you sort of think of that as then radiating. But we know that a gravitational wave does scatter off the black hole, it's absorbed.
Yeah.
But
Yeah, so I think one way to ask this is, we know that black hole super radiances event, you can
Yeah.
scatter things and get energy out of the black hole. Is black
I mean,
hole,
it's a torsional, sure, there will be some wave coming back out.
yeah, but is it sensitive to the shape of the horizon, or is it sensitive to multiple points? Which the tidal induced multiple zero.
Well, I'm just trying to get a physical sense of what this implies about how we think about the scattering wave, basically. Propagation of the wave. Back. Well, for example, if I have a neutron star, about a gravitational wave, the neutron star is getting out of the.
Yeah.
Shouldn't I think of the scattered wave as being particle radiation produced by the particle and higher order pieces of the potential view of the neutron star?
I guess I'm not sure why you're thinking only of the scattering problem, but one thing you can think of is a neutron star with the tidally induced quadrupole movement.
Yeah.
Will enhance the gravitational
Exactly.
radiation. Yeah, from the,
Yes,
from the
exactly.
binary. Yes.
Exactly.
So, yeah, so you can calculate that effect. And in fact, I have a calculation here, which I can just kind of give the punchline of. So if you go back to the quadrupole formula and you imagine now that your quadrupole moments, okay, are not just the orbital bit, but also now a stellar bit, right? You're going to have two of these. Then this is going to enhance the gravitational radiation from the
And
binary.
a piece is missing.
Exactly. That's exactly right. Yeah, that's right.
Yeah.
So in the black hole binary, so the effect of this is that your E dot, which I had written down before, is going to get an additional contribution. You're going to radiate gravitational wave, more orbital energy and gravitational wave. So a system with these tidal quadrupoles will reach merger before the equivalent system without tides.
Is it clear that they always add as opposed to?
Okay, so this is the other thing I wanted to mention. And I won't have time to go through it, but we've considered the impact of tides in the relativistic setting, but the same kind of tides that are present in Newtonian gravity. If you consider a relativistic treatment of the companion's gravitational field, okay, if you want to, in fact, a post-Newtonian treatment where you're expanding its gravitational field in powers of V over C, at the next order up in V over C, so the next level of relativistic treatment, you have a field equation that relates a gravitational vector potential to the mass currents in the tidal field. So basically, we've looked at the tides that are sourced by just the static, or slowly varying stationary mass distribution. But in the relativistic context, there's also a tidal field, which is sourced by the motion of the companion, this rho times its velocity. Okay, so this is sort of like a vector potential type thing in the Newtonian, in the post-Newtonian approximation. It will have opposite parity in terms of the perturbations than the electric part. So this is just like in electromagnetism. You have an electric field that produces a force QE on a charge, and then you have a magnetic field that is going to produce a V cross V type force. In the post-Newtonian regime, you get a similar decoupling into two sectors, which holds, for the tidal field because it's the companion is distant, the field is fairly weak. Anyways, what this means is you can decompose this guy into tidal moments, which instead of calling ELM, we might call BLM. And you can run through the same calculation. In this case, the relevant metric perturbation is the odd parity one. So we killed all the odd parity things except for this guy. And when you plug it into the field equations, you end up with a similar looking expression for what we would call HT, just with a single T, where it's proportional instead to the gravitomagnetic multipole moments. It's got some kind of Love number type amplitude here, which we'll call JL in this context. It's just to BLM. And, the functions here are different, but otherwise the structure is the same, where you can still identify a growing piece and a decaying piece. And when you calculate this guy by solving the perturbed Euler equation, everything inside the star, you actually find that these are negative generically for neutron stars. And this was a source of confusion in the literature, because if you hold the fluid to static, if you do not allow for velocity perturbations, you find that these things are positive. But the appropriate state for the fluid is actually one where it will develop some stationary velocity perturbations just from conservation of relativistic circulation. So if you imagine this binary in the infinite past being, widely separated so that this guy was isolated and it starts with no internal motions. When you bring them together and turn on the tidal field, there's a theorem that says that whatever circulation you had in the unperturbed state needs to be conserved as you slow it on and turn on the tidal field. And in order to conserve that in the perturbed space-time, turns out that you need some stationary fluid motions. Those stationary fluid motions enter on the right-hand side of Einstein's equation, Einstein field equations, which basically look something like this in the post-Newtonian approximations. They come in through here. And those are the things that make this gravitomagnetic love number negative. What this means physically is that the gravitomagnetic field sourced by this guy on this guy is going to induce fluid motions, which themselves are going to source a gravitomagnetic field that is going to counteract this. Exactly, it's the same thing as magnetic induction, Faraday's law, whatever from electromagnetism. And so that is an example where if you look at the total current quadrupole of the system, so some SJK, then you'll have a contribution from the individual current quadrupoles, but this thing will be negative. And so that will actually reduce the amount of power radiated in gravitational waves. This is a subdominant effect because it's a current quadrupole, mass quadrupole. I think it's a factor of V over C squared, maybe even V over C squared, I think, less important. So it's like a percent level correction.
But wait, are you saying, so physically, if I have a neglecting the loss of radiation, I can't have just a simple static tide without some additional.
If
motions with respect to the co-rotating in the co-rotating.
So if your companion is orbiting, if there's motion, that will induce motion inside the neutron star, inside the fluid motion. And there's no way to hold this perfectly static while satisfying Euler's equation if you believe the neutron star started in an initially static unperturbed state.
And it's invisible.
And it's invisible, that's right.
The assumption of no dissipation is important.
For sure. And that will break down close to merger. But for inspiraling neutron stars starting widely separated, it's a reasonable assumption. It's an assumption that everybody makes. So this circulation conservation I was describing, you can also get from you can see it from the curl of Euler's equation, which is something known as the vorticity equation. But it's basically, this was initially missed in the literature because if you don't consider what is the initial state of this binary in the distant past, you might just assume it's all scattered, right? And basically it boils down to there's a place in the Euler equation where you end up with the time derivative of something like an angular component of the velocity perturbation. And there's two ways for this to vanish. This could be time independent and it could vanish, or this thing could itself be zero. And that's it. This thing being zero is what corresponds to this circulation survey case. So if there is dissipation,
Just by traveling.
That's a good point. So I guess,
Well, this gets back to,
Yeah.
because it will be a circular orbit.
yeah,
No time dependence.
no, yes, that's right. So there will be a bit of lag due to causality, but there will be no other lag or lead if the star is you're treating a non-rotating tidal perturbation and your neutron star is invisible. In a black hole, that's not true because the black hole effectively has some viscosity or some internal dissipation because it can absorb things through the event horizon. So you get tidal heating, you get tidal warping. But those are not present for the neutron star, at least when you treat it this particular way. Okay, so I'm way over time. So, are there other last questions?
And I'm gonna,
So we've already detected this guy, like the love number, in the relativistic setting for the regular kind of tidal perturbation sourced by mass moments. The gravitomagnetic love number sourced by current moments is suppressed by one post-Newtonian order, and so it's much smaller. It's like 1% of the other. The effect is like 1% level. Than compared to this one. So I don't think there's any hope of directly detecting it soon. But if you simulate one neutron star perturbed by a tidal field that's varying in time like this, you should see this fluid motion get set up. And the pattern of fluid motion is actually an R mode. So an R mode in the relativistic context for a non-rotating star is just some stationary fluid perturbation with axial or odd parity. And that's exactly what's going on.
so what's the log number of the neutrons?
So in dimensionless terms, it's about 400, maybe for a 1.4 solar mass star. That's scaling things. I defined somewhere over here, this lambda L, but the lambda L has units because it depends on R. So you have to scale out a mass, okay, to make it dimensionless. And then it's about 400 for a 1.4, so that's neutron star. For the Earth, this thing is huge. It's like
there's part of the practice.
that's right.
Yours is like on 2 dimensions.
Yeah, so that's this one. That's this guy here.
So I wonder what is it compared to, but okay.
But you put in the factor of radius.
The Earth is defined here.
Yeah. So for neutron stars are much less deformed.
As he's defined the problem. The respective are.
Yeah. So the 0.2 is this thing, right? But then there's powers of R over M, and a neutron star is much more
Much more
compact.
than yours.
Yeah, exactly.
And the rest is-
Exactly.
Thank you.
Okay, yeah, thank you.